Hey Wheaton North, Mr. Yergler here. This video is going to take what we learned with galvanic cells and take it another step, talking about situations where we're not at standard conditions. So let's dive in. Here's two different cells. Notice that they're essentially the same, but there's a slight difference, right? One of them is galvanic, meaning one of them is spontaneous, and the other one isn't. I'm showing the electrons going from left to right in both cases. So let's start by figuring out what's getting oxidized and what's getting reduced. In the picture on the left, electrons, as shown, the electrons are going from the zinc to the copper, right? So what's getting oxidized? Well, ask yourself what's losing electrons, right? Because oxidation is loss. The zinc has to be losing the electrons, which makes it the anode, right? The consonants go together. Anode is always oxidation, cathode is always reduction. So on this other cell, we have essentially the same thing, but it's in reverse, right? And it wouldn't make sense for this to be spontaneous if that one's spontaneous, because if the electrons are spontaneously going to go from the zinc to the copper, then they're not also going to spontaneously go from the copper to the zinc. So again, what's getting oxidized and what's getting reduced? As shown, the copper would be the anode and the zinc would be the cathode. Now, we don't necessarily know which one of these is spontaneous yet. We could look on our potentials sheet and determine it from that, but there's another way we can determine it as well. I've shown you how to take that standard reductions potentials sheet and take the reduction and then you flip the sign for the oxidation, right? Here's another way of representing the same thing. The E of the cell is basically the electric potential of one half cell of the half cell at the cathode minus the electric potential of the half cell at the anode. It's still reduction minus oxidation. It's just another way of kind of showing it. So let's calculate this one on the left first. Copper has to be getting reduced, which we've already said. So that one stays the same, but the zinc is being oxidized, so we flip the sign on that one. Add them together and it comes out to 1.1 volts. For the one on the right, it'd be essentially the same but reverse, right? Zinc is being reduced, and so we leave that one the same. Copper is being oxidized, and so we have to flip the sign on that one. So it becomes negative 0.34, where it was positive 0.34 up here. Add those together, and it's the same magnitude, but now negative. So which one is the spontaneous one? This formula helps us to determine that. Delta G is equal to negative the number of moles of electrons transferred times Faraday's constant, which is 96,485 coulombs per mole, times the total E of the cell. So we'll do one calculation with the positive and one calculation with the negative. We don't actually have to do the calculation. Let me just kind of write it out. And you can see from looking at it that this one is going to give us a negative delta G, and this one is going to give us a positive delta G. Negative delta G is spontaneous, right? So a positive E always leads to a spontaneous reaction, and a negative E is non-spontaneous, right? So anytime you have a positive voltage, that's going to be a favorable condition, right, where the reaction will be spontaneous, it goes on its own. If you're given a situation where the E comes out to be negative, then that means it's going to require that much electricity to run, not give off that much electricity as it runs on its own. All right, so let's summarize all of what we talked about regarding favorability. Free energy, that's the big one. Negative delta G is favorable, positive delta G is unfavorable. Enthalpy, if a decrease in enthalpy is favorable. An increase in entropy is favorable, so positive delta S. Now equilibrium we haven't talked about in a while. Equilibrium, remember, is products over reactants, or the K expression is products over reactants. So a favorable reaction is going to be a really large K because you're going to have tons of products and very little reactants. And now voltage we can add to that as well. A positive electric potential is from a favorable reaction. So here's an example where we calculate delta G. I've given you an equation already. See if you can pause the video and calculate the delta G for this equation. You can go ahead and pause, it's all right. I'll wait. Okay, now that you've paused and figured out the delta G, let's go through it. I would start by writing out the half reactions, the oxidation and reduction half reaction. That helps you to figure out what the E of the cell is. We have to remember that we have to reverse the magnesium one because that's the oxidation one. So we end up with 0.71 volts. Now you can just plug that into your Gibbs free energy equation. The number of moles transferred is the number of moles that gets canceled out. We have to cancel out the electrons. And so even if you have a reaction where you're only producing 2 and you're producing 3 over here, you got to take them times like a least common denominator so that you have your electrons canceling out. So in this case, it's going to be 6 electrons times Faraday's constant times our voltage, and it's positive E, and so it's going to be a negative delta G, which makes sense, and it's 4.1 times 10 to the 5th joules. Now, so that's standard conditions, right? That's all we've talked about so far. And if you look at your potential sheet, it says standard reduction potentials at a certain temperature, and it has that little degree symbol, right, for the standard conditions. It doesn't mention that standard conditions actually also include one atmosphere of pressure and exactly 1.0 molar solutions. So what if we're not at standard conditions? Well, there's this what's called a Nernst equation. And I show you this not because we're going to do a lot of calculations with it. We're actually going to do 0 calculations with it. But it is helpful to kind of understand how voltage changes at non-standard conditions. Your energy at your non-standard conditions, so this would be non-standard, right? Notice that there's no little degree sign, right? Is equal to E naught, which is your standard conditions, minus some adjustment, right? So this is think of this as like an adjustment for your non-standard conditions. R is 8.31, T is your temperature in Kelvin, number of moles in Faraday's constant. And then the natural log of Q. Remember that Q is kind of like K, except we're not at equilibrium. So it's products over reactants, and only aqueous products over aqueous reactants. So to figure out how non-standard conditions are going to change your electric potential, you basically have to ask yourself, what changes would you make to the cell that would make it take it further from equilibrium? Because when Q equals K, you have a dead battery. No electricity is going to flow if you're already at equilibrium, right? The whole point is to be away from equilibrium so that you can have a reaction that progresses towards equilibrium so you can produce electricity. At standard conditions, your concentrations are all 1 molar, and so your Q would be 1 over 1, which is 0 with the natural log. So your E is equal to E naught, which makes sense because you're at standard conditions. If we want to be really far from equilibrium, we want conditions that are going to take us even further from equilibrium. And so let's imagine we make this solution even more concentrated. And this makes sense. The copper ion is a reactant, right? Because we're taking copper ions and we're plating them onto the copper. And so the more reactant you have, obviously, the more product you can produce. And the further away from equilibrium you are. So concentrations really just affect the Q. And so the larger your Q is, the worse it is, right? You want a really small Q, and that tends to up the electric potential. And a large Q, we can kind of think of it as impeding the electron flow. If there's very little copper ions in here, then you're going to kind of impede the electrons coming in and grabbing onto ions to plate onto the copper electrode. This is the main idea right here, of being able to predict how a different condition is going to change your voltage. Is it going to make it go up or make it go down? I like to think of it in terms of the Nernst equation, even though we don't have to do any quantitative calculations with that. You can also think about it as what makes you get further from equilibrium. What's going to allow you to produce even more product, right? The closer you get to equilibrium, your voltage starts to slowly decline. This leads us into another situation, what's called a concentration cell. A concentration cell has the same electrode and the same electrolyte. So if we look at this, we have a nickel electrode on both sides, and we have a nickel ion solution on both sides. You wouldn't think that it would do anything, right? It would just kind of sit there. But let's go to our Nernst equation. At standard conditions, our two half reactions are nickel ion going to nickel solid and nickel solid going to nickel ion. They would cancel each other out. But that's assuming that we're at standard conditions where we have 1 molar solutions. Think about what's the product and what's the reactant in order to kind of think about what's in Q. On the anode side, we're taking nickel atoms and going into solution. So the nickel ion here is a product. But on this side, we're going from nickel ion to nickel metal. So here, the nickel ion is a reactant. So products over reactants, this situation as it's shown is actually ideal because we have very little product and a lot of reactant, even though it's the exact same ion. So over time, this would actually produce electricity, but what's driving the electron flow is the concentration gradient. It's pursuing equilibrium, so to speak. And when it gets to equilibrium, where you have half a molar solution on both sides, then the electric flow would stop and you would have no voltage. Hopefully all that makes sense. If you have any questions, be sure to write those down, bring them up in class, and we'll get some practice there. All right, this is Mr. Irgler signing out.